Hi, guys. How are you guys doing? You guys are so darn cute. Even if I can't see you at school, at least I get to see you, pseudo see you, right? All right, we're going to get started. Good morning. I hope you had a good weekend. Couple things. First, we're going to take an exam tomorrow. It's exam 1112 online via my HRW. And I've given directions in your assignment section in Classroom. And I've also sent a stream about it. Just remember that it is a time test, so you cannot turn it in late. I'm giving you 15 minutes to take pictures of your scratch paper. Make sure you submit your scratch paper. If you do not submit your scratch paper, you will not get credit for the exam. So you must submit your scratch paper. Are there any questions about the exam tomorrow? 8 o'clock sharp. Make sure you set a lot of alarms. Can't miss it. So like I said, unless there's a police report or some type of doctor's note, so some type of extenuating circumstance, you must take the test tomorrow. You can't take it later. So make sure that you're taking it tomorrow at 8. Do you guys have any questions about the exam?
Are the questions timed or are only only the test timed?
Just the exam. Yeah, just the exam. The questions aren't timed. No.
Oh, okay.
So anything else? All right. Well, last week I was giving a prerequisite lesson to lesson 1.3, and that was an introduction to parent functions. So what I'd like to do right now is I want to do some math aerobics to get warmed up. So everybody has their video on, right? All right. So show me a horizontal compression. May, horizontal compression. Angel, I can see you guys. Show me a horizontal compression. Show me a vertical stretch. Vertical stretch. Vertical stretch. Bianca, you doing it? Yeah. Vertical stretch. All right. What about a reflection over the x-axis? So reflect over the x-axis. X-axis. Reflect over the x-axis. Good. How about reflection over the y-axis? Reflect over the y-axis. Right? Okay, show me a vertical stretch. What's a vertical stretch? What's a horizontal stretch? What's a reflection over the y-axis? Reflection over the x-axis. Give yourself a hand. Give yourself a hand. Give yourself a hand. All right. I did put some graph paper in. I tried to put graph paper for this assignment in there, but it's not any good. I think I sent a remind message to try to get some graph paper from the 9th because what I was trying to do wasn't working. Graph paper is no good. You're going to have to get some graph paper. Otherwise, it's going to be tedious. So let me just give you a brief summary of the parent functions. First of all, you need to know what functions, what equations match to what graphs. So in other words, when you look at a function, you have to know if is it a quadratic, is it a cubic, is it absolute value, and what do these look like? What does the square root function look like, right? What does the logarithmic function look like? What does the exponential function look like? So you need to be able to look at the function and know what its graph looks like. Another very important thing you have to know is what A, B, H, and K do to the parent. So you have to know what A, B, H, and K do to a parent. So A is vertical stretches and compressions and reflections over the x-axis. B is horizontal stretches and compressions and reflections over the y-axis. H is translations left or right, and K is translations up or down. And what we did last week is I had to look at functions, the transformations. We didn't get to the graphing. So I just want to talk about a couple things first. Okay, first of all, when you have an ordered pair, the reason why it's called an ordered pair is because it's ordered X and then Y. All right, so with H and K, if you have H, you're translating left or right, which means you're adding or subtracting from the X. When K is translations up or down, which means you would be adding or subtracting from the Y. Now notice what I'm saying. I'm saying adding or subtracting. So in other words, when you add and subtract, you're not changing the shape of the graph. You're just moving it, like putting your hand on it and moving it places. However, if you have A or B, you are not just moving it. You are transforming it. And that's why when we do a vertical stretch, it's like taking the parabola and stretching it up. When we do a vertical compression, it's like pushing down on the parabola, which is widening it out. With the parabola, when we do a horizontal compression, it tightens the parabola in. When we do a horizontal stretch, it pulls it out. So with A and B, you have to multiply to the variable. So since A is vertical, you would be multiplying to the Y. And since B is horizontal, you would be multiplying to the X when we're doing the point transformations. All right, so all we did is state transformations. So what we're going to do is I want to do some graphs with you. And let me write down the steps. I don't think I got this far with you. But in the problems you're going to work, I'm going to want you to do two things. I'm going to want you to state the transformation, which we practiced last week. So that's actually just writing in words. I'm going to want you to show the point transformation. And 3, you're going to graph. So let's take a look at a problem. They're just going to tell you to graph. I wanted to get my other notes. Just remind me, did I give you the order that you're supposed to translate left and right, stretches and compressions, reflections, and translate up or down? Did I give you the order last week?
Yeah.
Yeah.
Okay, perfect. Thank you. All right. Okay, so let's take a look at this. All right, so this is a quadratic. State the transformation. Is that left, right, up, or down?
Down 2.
Right. So remember, well, no, I don't think I did this. So the parent is the quadratic, the most basic graph. And you can pick any points off the quadratic. I'm going to show you how to make a little table here, though, to get the ordered pairs. So if I put in a -1 quantity squared is 1. If I put in a 0, 0 squared is 0. And if I put in a 1, 1 squared is 1. So these are ordered pairs. Left 1, up 1, 0, 0, right 1, up 1. Now, we don't have to pick those points. Those are just the most simple points. And this is the parent of the quadratic, left 1, up 1, 0, 0, right 1, up 1. So this is what the parent of the quadratic looks like. Now, we're always going to use these points when we're doing a transformation on the quadratic. And like I said, you don't have to use these points. You could have put in a 4, and 4 squared is 16. So these are the points we're always going to use for the quadratic. So when we go down to, the x value stays the same. So down means -2. So -2 plus 1 is -1. 0 minus 2 is -2. And 1 minus 2 is -1. And from there, we do the graph. So see how we're going to be doing it? All the problems, we're going to state the transformation. These are the transformational points. And then we're going to graph. So let's see if the graph looks like the parent translated down to. You should always label the axes. Mr. Johnston will flip out in calculus if you don't label the axes. And I really want you guys to get in the habit of not reading these like -1, -1. I want you to read it left 1, down 1, 0, down 2, right 1, down 1, so there's no confusion. I don't want any points graphed incorrectly at this point. So you're going to always read the x left or right. You're going to always read the y up or down. So the first point is left 1, down 1. The next point is 0, down 2. And the next point is right 1, down 1. So there's your quadratic. And we know this is right because this is the parent shifted down 2. Let's do another problem. By the way, my board is damaged right here. So these are GK's board, and somebody hit the board here and chipped off. So if you're wondering why is that, why won't I ever erase that? It's damage to the board. And I tried to put a white fingernail polish on it, but it doesn't work. So that right there, it's not a decimal or anything else. It's the board's damaged. Okay, this is definitely a quadratic, and we don't need to draw the points out again. In fact, we could do the points in our head. So we put in a -1, quantity squared is 1, 0, 0, right 1, up 1. So those are the parent points we're going to use for the quadratic. The first thing you want to do is state the transformation. So it is a quadratic. We know what it looks like. What would this transformation be?
Left 2.
Good, left 2. So left 2. So remember, this is not in the form. The form would be x minus a -2, which makes it left 2. And now what we're going to do, left means the x. So the x's are going to change this time. The y stay the same. So left 2 would be -2 and -1 is -3. -2 and 0 is -2, and -2 and 1 is -1. So when we graph it, we're expecting the parent to have translated left 2. So this would be left 3 up 1. This would be left 2 0 and left 1 up 1. And sure enough, that looks like the parent that was translated left. Now, after you do a million of these, you can just look at it and tell. You don't have to do any of this work. So like on the SAT, you might look at this and go, oh, that's the parent, shifted left 2, pick A, B, C, or D. You're just going to look and pick the graph. So the only reason I'm showing you this is because we're just starting out, but eventually you'll be able to look at this and go, oh, this is the quadratic parent, shifted left 2. Pick the answer. Let's do something more complicated now. So we like transformations. We don't have to do an input-output table. These are quick graphs. So when they're in the form that I gave you, we can graph almost in our head of what's going on. This one, a little bit more tricky because there's more than one step to it. All right, now you want to state the transformation, but make sure you state it in the correct order. So what is the correct order? It is a quadratic sum. So we are going to use left 1, up 1. So students have asked me, do you always use these points? Yeah, for the quadratic, but square root is going to have different parent points. The cube root is going to have different parent points. The cubic has different ones, exponential, logarithmic, they all have different parent points. All right, go ahead, I'm waiting. State the transformation in the correct order. Somebody.
Isn't it to the left 2?
Oh, hold on. This is outside the square. So that's not, I'll write it in the form for you to give you a hint. The form looks like this.
Yeah, so it's up 2.
But yeah, you gotta follow the right order though. Follow the correct order.
Gosh. Okay, so it's compression or a stretch or compression.
Vertical stretch. It's a vertical stretch by 3.
How do you know when it's vertical or horizontal?
When it's outside, when it's A, it's vertical. When it's inside there, it's horizontal.
So it's a
So
vertical.
this number is outside the square, so that's A. When it's inside B multiplied to X, it's B.
Okay,
So this is a vertical stretch by 3. What's this mean?
Reflection over the x-axis.
Yep. And what's that mean?
Up 2.
Okay, does anybody have a question about that? So I'll write the form over here. Remember the form is A times the quantity bx minus h squared plus k. So remember A is outside the square, vertical stretches, compressions, reflection over the x-axis. K is up or down. B, horizontal, stretches or compressions, left or right. And remember with B, you have to take the reciprocal. I went over that, right?
Yes.
Okay, so here we go. So vertical stretch means we're going to multiply the y by 3. So that means the x stays the same. And we're going to multiply the y by 3, multiply the y by 3, multiply the y by 3. Reflect over the x. Watch my arm. That's a y movement, isn't it? Isn't that an up and down movement? So we want to negate the y. So whatever the y is, negate it. So if it's negative, make it a positive, positive, make it a negative, make it a negative. And the last is 2, which affects the y. So we add 2 to the y. And I know this seems tedious, but it's not. Once you get going with this, it's so easy. So up 2 would be negative 3 plus 2 is negative 1. 2 plus 0 is 2. 2 plus -3 is -1. Let me do the graph. Have your calculator ready, because this time we're going to put it on the calculator and check to see if we did it right. So this is left 1, down 1. This is 0, up 2. This is right 1, down 1. So the first thing we're going to do is see if this makes sense. So first of all, a vertical stretch looks like this, right? So does this look like it was stretched? Remember the parent? The parent kind of looks fat. So that does look like it's stretched. And it was definitely reflected and up. So we have a high level of confidence just by looking at it that we know it's right. But now we're going to put it on the calculator. So this is what you do. You go to this y equals up here on the left, and you clear everything out and put this in. Now the negative key is the white one down here. So you put -3, x is next to the alpha key. So x squared plus 2, and hit graph up here in the blue. You guys see that? So now we actually verified with the calculator. You can't graph on a test like this. I mean, you have to do because you have to turn in your scratch paper, you have to do it by hand. So I'm going to want you to write the statement in the correct order. I'm going to want you to show me the point transformation, and that you can't just put it on the calculator and give me the answer. So, all right, so while we're here, let's do the domain, range, and in behavior, since that's not going to go away. So after Tuesday's exam, it's not going to go away. It keeps coming back. So what's the domain here, class? What's the domain in interval notation?
Negative infinity, comma infinity.
Yeah. What's the range?
2, comma negative infinity.
Yep, negative infinity up to 2 closed. And then the end behavior is as x goes to the right forever, what's the function doing? As x goes to the left forever, what is the function doing? So what's happening on the right?
Negative.
It's going down, right? What's happening on the left?
It's going down as well.
Good. Good job. So like I said, this seems really tedious, but you're going to be doing this so fast. And then eventually, when you get used to seeing this, you're going to be doing it in your head, basically. Okay, now.
Serge, I have a question.
Go ahead.
When I put the calculator on y equals, it's just like y1 equals. It's. How do I show it? I don't know if you can see.
Yeah, y1 equals, and all you're going to do is put in this negative down here, -3, and then the x is next to the alpha key. X squared, I use this x squared over here, plus 2. And then you hit graph.
It doesn't, it just. Oh, okay, I got it.
You got it?
Thank you.
Okay. All right, so I think we went through stating these, right, out loud. But now what I'm going to want you to do is I'm going to want you to do these steps on this practice and exam. This is not an exam. I'm calling it an exam, but it's because I used to give this as a quiz, but it's just practice right now. You guys are going to do those, and that's due on Wednesday night at 11:59. Would anyone like me to do any of these problems, or do you want me to work another problem?
Can you just do one of those so we could see how you want them done?
Sure. I would definitely use graph paper because it's a lot of graphing. And you don't want to draw the graphs out like I'm doing every time. It's tedious. I tried to send you graph paper that you could duplicate, but it's just not working out. So at the workshop, I had one of my students take a look at it and see how it looked, and it doesn't look good, the graph paper. It's pretty cheap if you get it at the 99-cent store. Dollar Tree or whatever. All right, let's do one of these. I'm making this up. Okay, so state the transformation. Go ahead, Miss Thing.
You would go right 1, a reflection across the x-axis, and then up 3.
Yep. So this is a quadratic, so I'm going to use those points that we chose for the quadratic. Now remember, if you forget these points, all you have to do is put numbers into x squared and figure it out. So you just put them in an input-output table. So here we go. So right 1 means add 1 to the x. So add 1 to the x, add 1 to the x, add 1 to the x, leave the y's alone. Reflect over the x is a vertical movement. So that means negate the y. So the x's stay the same. 0, 1, 2. Negate the y, negate the y, negate the y. And if it starts out negative, you make it positive. Okay, up 3 means add 3 to the y. So add 3, add 3, add 3. Let's graph those. So this is what I was saying. When you're moving just left and right or up and down, you're adding to x or y. When you are doing a vertical stretch or compression or horizontal stretch or compression, you multiply to the x or y. All right, so this is 0 up 2, right 1 up 3, right 2 up 2. Now let's just see if this makes sense. Does that seem like it was shifted right? Yes. Does it seem like it was reflected? Yes. And was it shifted up 3? Yes. And then we can put it on the calculator too. So on the calculator, you go into y equals, and this negative is the white key, parenthesis, the x is next to the green key. Now we're using the minus key, which is the blue key, 1, close parenthesis, and then raise it to the second power, and then add 3 and hit graph. So I didn't have it in the equation editor, so let me do this again real quick. Negative parenthesis x minus 1 squared plus 3. Sorry about that. That's what it looks like.
Mine shows up as it going off the screen.
It's going off the screen. You need to reset your calculator. So we can reset it right now. You go to, see the second key, the yellow key? Go second mem, the plus key, go second mem. And then hit number 7 for reset. And then hit 1 for all memory. And then hit 2 for reset, and that should fix it. The calculator has a window, and if you change the window settings, it can move the window somewhere else. So you can always reset the calculator by hitting second mem, right? And just following the steps to reset the calculator to the default settings. All right, do you guys have any questions about
It works now.
graphing? Oh, it does? Okay, good. Let's do one more with something that's horizontal. You don't have a lot of these because your book, I guess, is afraid to put them in there, but you should know how to do them. So see how this is inside now? And remember with B, you have to take the reciprocal. So this isn't a horizontal compression. This is a horizontal stretch by 2. That is a reflection over the y-axis. And that's down 3. So once again, this is a quadratic. So those are the parent points. Horizontal stretch means multiply the x by 2. So multiply by 2, multiply by 2, multiply by 2, and the y's don't change. Reflect over the y. That is a horizontal movement. So horizontal means negate the x. So negate the x would make it positive. Negate the x makes it negative. 1, 0, 1. And last but not least, down 3 means subtract 3 from the y. So negative 3 would be negative 2, negative 3 would be negative 3, and negative 3 would be negative 2. Now, tomorrow when you take the exam, you're going to enter from classroom, right? Because like I was trying to tell you that by entering from classroom, it knows who you are, trying to go into my HRW. If you don't know how to take pictures of in your phone and upload them to Classroom, if you look at resources, I provided a short video that shows you how to do that. Make sure you take pictures of your scratch paper though. Some people are like, well, I forgot my scratch paper. And I said, well, I just had to give you a 0 because I have to have the scratch paper. So this is right 2, down 2. This is 0, down 3. And this is left 2, down 2. Let's make a little fatty. So horizontal stretch, right? Pull. So you took the parent and you pulled him out. That looks right. Reflect over the y. reflection over the y doesn't do anything to the parent. And then down 3. So I have a high level of confidence we did that right. And you could put it on the calculator if you wanted to. To put this on the calculator, you would use the negative key at the bottom. This is 1 divided by 2. So parenthesis, white key, 1 divided by 2, x, quantity squared, minus, that's the minus key, 3. So the negative key and the minus keys are 2 different keys, so the calculator doesn't get confused. All right. All right, I have to go outside for just a moment. So I will be right back, but I'm going to teach a new lesson. So we're going to talk about 1-3 now. So this was all a prerequisite for 1-3, but let me just run outside for just a second. I have a gardener trying to ask me questions right now. I'll be back in. All right, I'm back. Okay, anybody want to ask me anything up to this point? Okay. I don't want you to look at the book on this. The book is so confusing. And if you saw my book, I just put X's through all these pages. So we're going to do the assignment, but I don't know what they're trying to say in this section at all. So don't read the book. All right. So do not read the book on this lesson 1.3. Okay. Now, the way I introduce transformations is looking at the quadratic. Okay, now we're not looking at the quadratic at all. We're looking at just a general function. And what I mean by that is this is a function that would work for anything. And I'll just show you what it looks like. So it looks really similar to the quadratic, but this is any function. So see this, a times f of x. And this f of x could be a quadratic, it could be a cubic, it could be a cube root, it could be anything. But so that's why I wanted to show you the quadratic. So I wanted you to see something concrete. So now we're just talking about any function. I'm going to erase this side of my room. Okay, now this function that I'm going to do, it does not have an equation, but it does pass the vertical line test. So see how they write it? See, the other day or this morning, you saw me write it like this, right? Or earlier. So this isn't a quadratic though. This is just any function. So what would you think this is? Do you think this is left, right, up, or down?
Up 4.
Yep, it's up 4. You're absolutely right. And so let me show you this function. It looks like this. Left 1 down 2, right 1 up 2, left 3 down 2, and 5, right 5 up 2. So this is what it looks like. And that is a function. Remember that's nothing, that's my damaged board. It does pass the vertical line test. So this is a function. And it's like, okay, she just told me to use left 1, up 1, 0, 0, right 1, up 1. That's for the quadratic though. So what points do you think I can use for this function? Go ahead, I'm listening. Could you just use any points on the graph? So give me some points you see on the graph. Go ahead, I'm listening.
1, 2.
Yep.
Oh, yeah.
Right 1, up 2. Go ahead, I'm listening.
-1, 2.
Left 1, down 2. Please read them like that, please. Okay. Left 1, down 2. Go ahead. What's this one?
Right 3, down 2.
Good job. And what's that one? Right 5 up 2.
Right 5 up 2.
So that's all we do. Is it's not a quadratic, it's just some function. We could just pick points off the graph and go up 4. So up 4 has to do with the y. So up 4, so plus 4 would be 2, plus 4 would be 6, plus 4 would be 2, and plus 4 would be 6, and there's our points. Now, what you're going to do is you're going to make this parent dotted because he's not really there. We're just using him to help us out. So it's dotted, which means it's really not there. And we're going to go left 1 up 2, right 1 up 6. It's right up here somewhere. Right 3 up 2. Right 5 up 6, and do our graph. So that looks like it was up 4, right? See, it's like I took my hand. You did this in geometry. It's like I took my hand and moved it up. So I took some of these points. Obviously, this graph has infinite points, but I just took some easy points and I just used them to show the translation up 4.
How did you know it was like a zigzag thing line?
It was given. This was given.
So it's,
No,
oh,
it's not going to always be like that. It could be a zigzag. It could be a half of a circle. It could be anything. This is just a graph that I have. It could be anything.
okay.
Right now, I'm just showing you like a zigzag, but it could be anything. So once again, we don't have a quadratic. They're giving us a function, and they're saying f of x minus 4. So take a guess what that is. Do you think that that's left, right, up, or down?
Right 4.
Because that's h, right? So they give you this function, Once again, it looks like a zigzag, but they don't all look like this. So this would be so these points again, oh, it's the same one. Left one down 2, right one up 2, right 5, right 3 down 2, right 5 up 2. So this is what they gave as the problem. And like I said, this is the parent, so we want to make it dotted. It's not really there. And it's just like we're going to take those points that we see, left one down 2, right one up 2, right 3 down 2, and right 4 up 2. So those are just points that represent the graph. And now right 4 means add 4 to the x. So add 4 would be a 3, add 4 would be a 5, add 4 would be a 7, add 4 would be what, an 8? The y values stay the same. So when you graph these, you get right 3 down 2. So right 3 down 2 would be here. Right 5 up 2 would be there. Right 7 down 2 would be there. And right 8 up 2 would be there.
Miss Birch,
Yeah.
isn't your x for the last point 5 if it's the same one as last time?
5. And then when you add 4, should be 9. Thanks. So this last guy, 3, 4, 5, 6, 7, 8, 9. Right 9 up 2. So he was a little off there. Thank you. So does that look like the original graph or the parent shifted right 4? Sure does. Now, you were asking me, do they all look like this? And so I'm just going to pick a problem where it doesn't look like this. I'll pick one out of your book. So look at page, take a look at page 41, number 2. Actually, 41, number 1. Page 41, number 1. Okay, now they actually don't even give directions on this. It's ridiculous. This section, I think somebody fell asleep when they were writing it. It's really bad. So this looks like left 3, 0. So I'm graphing the parent. It looks like what, 0 up 3. And right 3, 0. And it looks like this half of circle or half an arc. So that's the parent, and it is a function. It does pass the vertical line test, but it doesn't have an equation. So I'm going to make it dotted because it's not really there. We're just using it to graph. And we would say to ourselves, well, okay, that's fine, but what points are we going to use to transform? So what points would you use?
Zero, negative, negative 3, 0.
Left 3, 0. Go ahead.
Up 3.
0 up, 0 up 3. What would this be?
And then
Right.
left 3,
Well,
0. Oh, yeah, right.
right 3,
Right
0.
3, 0.
So this is how I want you to read them. This is left 3, 0, 0 up 3, and right 3, 0 as ordered pairs. All right. Now, notice that they don't even tell you to graph. Look what they say. They say, write g of x in terms of f after performing the given transformation of the graph. It doesn't tell you to graph. You are graphing, though. It should say graph g of x. So we are graphing here. Okay? All right, so it says on this, it says translate the graph to the left 3 units. So left 3, left 3, left 3, left 3, left 3, and the y value stays the same. So this is actually a problem right out of your book. All right, so read the first one to me, please.
To the left 6, 0.
6, 0. Left 6, 0. This would be what? Left 3, up 3, and 0, 0. Does that look like it was translated left 3?
Yes.
Yes, it does. So while we're here, they're not asking for this, but I just want to practice. What's the domain?
-6, -3.
Closed on -6 to -3, closed. Actually, no. That's not it. -6 to what?
0.
0, 0, yeah.
And what's the range?
0 to 3.
Closed on 0 to 3, closed, right. So that's your domain and range. Range is closed on -6 to 0, and that's the domain. The range is 0 up 3. Okay, do you guys think you understand how to graph just a plain function?
Yes.
Okay. Okay, also in this chapter, there's a bunch of things I'm not even sure if I'll be able to get through everything. I'm going to try though. Now I want to talk about even and odd functions. Okay. We're not going to use this a lot right now, but I'm going to introduce an even function. And an even function says this. If you put a negative into the function notation, it's going to come out to just be f of x. I'll explain it in a minute. An odd function, when you put a negative into the function, it's going to turn out to be negative f of x. So a function is not necessarily even or odd. It can be neither. But let me talk about these real quick. Even functions are symmetric about the y-axis. An even function would be the quadratic. So the quadratic is symmetric. It's a mirror image across the y-axis. It's an even function. So it's not just even because of the power. It has to be It has to be symmetric about the y-axis. Okay, an odd function I'll show you how to test for these. An odd functions are symmetric about the origin. I'm going to show you some examples of these, I think. All right, let me show you. So they're going to ask you, is the function even or odd? And sometimes they'll give you a graph, but sometimes they'll give you a function. So I'm going to do a few of them. The graphs are easy because if you saw this, all you do is just look at it. So isn't that symmetric about the y-axis? So you would just say it's even because it's symmetric about the y-axis. Always give a reason. What about this guy? Now that's some weird function. We don't even know what this is. But first of all, it's not symmetric about the y-axis, and it's definitely, you don't know anything about origin symmetry, but it's not symmetric to the origin either. This would be neither, no symmetry. Okay, this right here, this is the sine curve in trigonometry. And I didn't draw it very good, but that is odd, and it's symmetry about the origin. So this is odd. Okay, I'll tell you why. Watch this. If this point right here was right 1 down 2, this point would be left 1 up 2. So see how they're exactly opposite? That's symmetry about the origin. So let's say this point right here was, I'm just making this up, let's say it was left 3, 0. This would be right 3, 0. They're exactly opposite signs. So when the signs of the ordered pairs are exactly opposite for both x and y, that's symmetry about the origin. Okay, now those are easy because you could just look at the graphs. What if they don't give you a graph? So if they give you a function, we want to be able to test for the symmetry. So symmetry sometimes helps us with graphing, especially more complicated problems. So check this out. Let's say they give us a function. This is actually a quadratic that's vertically compressed by 1/2. Here's what you're going to do. Is it even or odd? You always put in a negative x and see what happens. So wherever you see an x, you're going to put in a negative x and work the problem. So this would be 1/2 x squared. And since putting in a negative, put out the function f of x, since they're the same, that means it's symmetric about the y-axis. So remember the definition for even? I said if you put in a negative and you get out the function, it's going to be even. So that is an even function. Let's try another one. Now, when you first glance at this, this looks even, but it's not. Watch. When you put in a negative x, so it is a parabola, but watch. When you put in a negative x, you can't deliver that power across the sum or difference, and that does not match the function. It's not even exactly opposite. It's nothing. So it doesn't match the function, and it's not exactly opposite. So this would be neither. Let's do so once again, we don't have a graph. So when you put in a negative x, this would be negative x quantity squared. And this turns out to be x squared because the negative is part of the power. That's exactly like the function. So that would be even. And that is symmetry with the y-axis. And when you just even think about it, this is the quadratic shifted down 3. It still keeps its symmetry. So shifting the parabola up or down keeps the symmetry with the y-axis. It's shifting it left or right that's going to destroy the symmetry. Okay, hang in there. I got one more thing to teach. And we're actually going to look at some real life problems and write the function that matches the real life problem. I am not teaching this like the book. You're going to have to do this about 1 million times in this class with different functions. So make sure you ask me if you have any questions. Okay, can you guys look at your book, please, on page 38, example 2. Okay, so let me just tell you what we want to do. When we look at a word problem, we want to analyze it, we want to make a plan and solve it, and then we try to justify our answer. So 38, example 2. Okay, I'm going to read this real quick, if you just bear with me, okay? An old stone bridge over a river uses a parabolic arch for support. In the illustration shown, the unit of measurement for both axes is feet, and the vertex of the arch is point C. Find a quadratic function that models the arch and state the function's domain. So I'm just going to draw the arch. And I'm going to put these points down. So they're saying that point A is right 2 down 20. point B is right 52 down 20. And point C, which is the vertex, is right 27 down 5. Now, point C being the vertex is HK. So HK is the vertex. That's how the vertex is defined. So you might want to make a note that the vertex is defined as HK. So the directions say find the quadratic function. And they say quadratic, so we know that it's a quadratic. And then it says to state the domain. And we will do everything in interval notation from here on out. All right, so we're gonna look at this information, understand the problem. We're gonna have a plan, and I'm gonna show you the plan right now. Now, remember what we just did. We just looked at a general function, and it looked like this. And I didn't put the B in, but I'm gonna put it in this time. So this goes for any function. Cube root, square root, absolute value, logarithmic, exponential, A, B, H, and K. So they straight out told us it's a quadratic. So now I'm going to write the quadratic function. It's A times bx minus h quantity squared plus k. So they straight out told us that it was a quadratic. And now we're just going to find A, B, H, and K. Well, we already know H and K. It's the vertex. So we already know that H is 27 and K is -5. And if you look at this problem, there is no B. So that means B is 1. So if you look at what they're telling you to use, they're telling you to use A times f of x minus h plus k. So that's saying that B is 1. So don't you believe that if we find A, we can write the function? So here we go. So what we're going to do is we're going to write a function. And we're looking for A, so we don't know what it is. And we know that B is 1. So it's 1x. And we know that it's minus 27. And we know that K is minus 5. So think about it. Can't we take one of these points, like A, an easy point? A. And wouldn't that be an XY ordered pair? So if we want to compute the function when x equals 2, wouldn't this just be a label? And isn't this really y, which is -20? So aren't we able to put in that x and y into this function and find A so we can write our function for this problem? So this would be -25 quantity squared minus 5. So I'm simplifying this down. So this would be -25 times -25 is 625. A. Solve it. So you're going to add 5 to both sides. So when you add 5, this becomes what? -15. And then we're going to divide by 625. So we found A. It's negative. If you divide the top and the bottom by 5, you get 3 over 125. And now we can write the function. So the function that represents this bridge problem is A times B is 1 times X minus H plus K. And I promise you, if you put that in the calculator, you will get this graph. Now they want to know what the domain is.
I have a question.
Hold on.
Oh,
So the domain is from here to here. So the domain would be from 2 to 52. All right, go ahead.
Oh, how did you not get A, but how were you able to get B and H when they all had the same? We used coordinates for all of those, but you weren't able to find A in the beginning. That's what I'm confused on.
We don't have A. You can't, this information doesn't give us A. So because they gave us this function with B missing, we absolutely know that B is 1. And since the vertex is HK, we know that H is 27 and K is -5, but we cannot determine A from this information. So this is why we have algebra, because we know we have 4 unknowns and we know 3 of them. And if we know 3 of them, we can find the 4th one. And this would take forever to guess this, but we're using algebra to determine it. Now, what I want to know about is, do you understand that we're finding when X is 2, Y is -20, right? When X is 2, Y is -20. So what you see me doing here is you see me evaluating the function for X, and this is just a label. So I'm taking the label out for Y and I'm putting the actual Y value in, which is -20. So in other words, I'm using this point A, and you could use the other point. If you use B, you're going to get the same answer. I just used the easiest point to find A, and then after I found A, because I knew everything else, I was able to write the function. And if you put this on the graphing calculator, you will get this graph. Okay, do you want to ask me a question? Because I'm going to prove to you that this is right. Because what I'm going to do now is I'm going to take the other point and I'm going to justify my answer. I'm going to prove to you this is right by using the other point now. Does anybody want to, I'm going to erase this. Is that okay? But let me just tell you, we're always finding A, B, H, and K, and I'm always going to write it like this in all the problems that I do for all the different functions.
Miss Birch, when you subtracted 15 from both sides, wouldn't it be 5?
I didn't subtract 15 from both sides. I added 5. So right here, I added 5 and it went away, and I added 5 as -15.
Oh,
And then I divided both sides by 625, and I simplified this fraction by dividing the top and the bottom by 5. So check this out. I'm going to take the function that I came up with, and prove that this is right. So if I want to bet some money, I know that this is right. Now watch what I'm going to do here. I'm going to take the other point B and prove that this is right. So I'm going to take G of 52. So wherever I see an X, I'm going to put 52. And the answer I'm going to get is going to be -20. So watch. 52 minus 27 is 25. 180 squared. 25 squared is 625. And I'm going to put it over 1 because I'm going to cross cancel. So 125 goes into itself once and it goes into 625 5 times. And so this ends up being a negative 15 and a negative 5, which is negative 20. And look at that. So when x is 52, y is negative 20. And now I absolutely know this is a proof that I did this right. So I use the 1 point to write the function, and I use the other point if I wanted to. I'm not going to make you do this, but you can use the other point to justify your answer. So I didn't accidentally come up with negative 20. I mean, this is right. So that says that that function is right. Now, I was actually going to do another problem, but I think this is enough for today. This is enough to chew on. So what I want you to do is make sure you do this right away. The practice in the exam where you're stating. I did put these answers in classroom where you have to state the transformation, show the transformational points and graph. So all the answers for the practice in the exam are in classroom. I opened them up this morning. Okay, but obviously I'm not going to work a lot of these problems. So if you have a question, ask me now. So who wants to ask me a question about these problems? Because if you come into class on Wednesday, I'm going to do another one, but that's it. You have to ask your questions now because obviously these problems are too long for me to work. So if you have a question, ask me now.
Ms. Birch, how did you get the 5? Or like, what is the 5 that's on top of the 625 when you're doing the proof?
You know how when you have fractions like 2/4 times 6/9, you know how you can cross cancel? 2 times what is 4, 2, 2 times what is 6, 3. I'm cross canceling fractions. So
okay.
I did the order of operations, I'm cross canceling. So I'm dividing this by 125 and getting 1 and dividing that by 125 and getting 5. So 125 times 1 is 125 and 125 times what gives 625, that's 5. And so then negative 3 times 5 is negative 15 minus 5 is negative 20. So I'm multiplying, I'm cross canceling, I'm multiplying fractions. Go ahead, what else? So on this, you would just put a check because that's a proof. So we just prove that's right. So basically, you're picking a point, and wherever you see X and Y, you're going to put it in, and you're going to solve for the unknown. Once you solve for the unknown, you write the function. And then if you want to check yourself, you could use the other point in the function to show that you can come up with a point 52 down 20. Any questions? The best thing to do is you have this written down, see if you can do it. So see if you can go through the steps and do it. Because you're going to have a lot of these. So if you think that, oh, well, I'm not going to worry about it because she's only doing this. No, you're going to do about 50 of these in this or more, 100 of them in class. So you have to know how to do this. So if you have any questions, make sure you ask me. And like I said, I would make sure that you can do this on your own. Just take this example and try to do it on paper, scratch paper, and see if you can do it on your own. Because if you can do this one, you're going to be able to do the other 100 that I give you. So there's going to be a lot of these, and almost every single chapter, every module has this in it. They're just different functions. So instead of the quadratic, you might have the cubic. Instead of the cubic, you might have the absolute value. So you're just doing them over and over again. You do them all the same way though. All right. I will see you. On Wednesday. Have a great day. You can hang out with me if you want. I'm going to turn the recorder off though. But you can ask me questions if you want. Okay. Have a good day.
Miss Birch, so let's say that the B was given to you